Hi, this is Thomas. Welcome back to math class. We're continuing to look at the topic of differential calculus, and today we'll be learning about the concept of evaluating stationary points. Using derivatives to analyze characteristics of the original function. Stationary points can either be maximum points on a curve, or minimum points on a curve, or inflection points on a curve. So as an example, I might have, looking at a limited range of a function, I might be looking at the following pattern of the function. And I have a turning point, which is a maximum to the left of the x-axis. I have another turning point, which is a minimum to the right of the left of the x-axis. And then I have in the right around the origin, I have an inflection, which is where the curve goes flat, but it doesn't change direction. It simply changes its behavior. So it was increasing in slope, and then it began to decrease in slope at the point of inflection. And we're going to learn how to evaluate the derivative of the function to identify and classify stationary points. Let's look at an example. We have a function f of x equals 2x cubed plus 3x squared minus 12. And our first step is the derivative. Let's take the derivative of this function using our constant multiple rule and our power rule. We end up with 2 times 3, 6x to the power of 3 minus 1, 2. Plus, again, same rules, 3 times 2, 6. X to the power of 2 minus 1 is 1. And the negative 12 will become 0 and fall away. Once we calculate our derivative, we want to identify our stationary points. And the stationary points are the points at which the output of the derivative is 0. So I'll set my second derivative equal to 0. 6x squared plus 6x. And I can solve for x. 0 equals 6x times x plus 1. Factoring out the common term. And now there are two possibilities for x. Either 6 times x is 0, or x plus 1 is 0. Thus, x can be either 0, in the first case 6 times 0 is 0, or negative 1. In the second case, negative 1 plus 1 is 0. Either of those will make the equation true. Now step 3 is evaluate stationary points. And I have two options for evaluation. One is a sign diagram, and the other is the second derivative. So let's look at our first option, the sign diagram, to begin. I'll create a sign diagram with the zeros from my evaluation of the first derivative, and those values were 0 and negative 1. And I'll pick test values on either side of each of these zeros. So a value less than negative 1 is negative 2. A value greater than negative 1 but less than 0 is negative 1/2. and a value greater than 0 is 1. And I'm going to test each of these three values in my derivative. The derivative input of -2 and the derivative input of -1/2 and the derivative input of 1. Now I'm simply looking for the resulting sign, so I don't need to do full calculations. I can instead think about the number properties associated with these operations. So for example, in the derivative is 6x times x plus 1. And if I input the value -2 times 6, I'll have a -12. So negative, and then I'll be multiplying by x plus 1. -2 plus 1 is negative. So the resulting value is going to be a positive. That's what I need to know. I don't need to know the value. I need to know the sign. Now let's do the same with the input of -1/2. -1/2, 6 times -1/2 is also going to give me a negative. Then -1/2 plus 1 will give me a positive, and the result negative times positive is negative. And then the same analysis with the input of +1. Now 6 times +1 is positive, times 1 plus 1 is positive, so positive times positive equals positive. And I can now put these signs into my diagram. At -2, I'm positive. At -1/2, negative. And at 1, positive. So now we have the signs that we're looking for before and after each of the zeros. And the sign diagram of the derivative helps us to understand the shape of the original function. When I see the sign diagram goes from positive to negative, the 0 of -1 is the turning point where I'm going positive to negative, and there I have a maximum. At 0, I'm going from negative to positive. There I also have a 0. This is a minimum point. So on the left I have a maximum, and on the right I have a minimum. -1 is a max, and 0 is a min. So using the derivative, I've calculated the x values of the coordinates where the original function has a maximum and where it has a minimum. Now what I want to know is what are the actual points on the original function. So I need to use these x inputs into the original function to calculate the y values, so I know the precise points of the maximum and minimum on the curve. Before I determine the precise points in the original curve, I want to look at my second method for evaluating stationary points. And the second method is step 3b, which is the second derivative test. We use the first derivative to evaluate the turning points using the sign diagram. Now what I'm going to do is I'm going to take the second derivative and evaluate the points based on the resulting output when I input the zeros from the first derivative into the second derivative. So first let's calculate the second derivative. This is going to be f double prime x. Looking back at our first derivative, the first term is 6x squared. So we will use our constant multiple rule and the power rule to multiply 6 times 2 to arrive at 12x. And the same for 6x, which will become 6. So now I have my second derivative, and I'm going to input the zeros that I've calculated in the first derivative as my stationary points. In step 2, I calculated 2 zeros based on my analysis of my first derivative, and now I want to evaluate these x values as inputs into my second derivative. And as with my sign diagram analysis, with my second derivative test, I only need, this is the second derivative test, I only need to know the sign of my output. So in this case, because I am adding 12x plus 6, I'm going to actually need to calculate the value. I didn't do that in the sign diagram test. I simply calculated signs. With multiplication and division, you can do that. With addition and subtraction, you generally need to work through the full calculation. So 12 times -1 is -12, plus 6 equals -6. The key is the value, the key is the sign negative. This means that at the point -1, I have a maximum. Because with the second derivative test, if my output is less than 0, the point is a maximum. And evaluating the input of 0, 12 times 0 is 0, plus 6 equals 6, and a value greater than 0 means I have a minimum. Now, in this particular function, we don't have an inflection point. The way we identify an inflection point is only with the sign diagram evaluation. We can't identify an inflection point with the second derivative test. In the sign diagram, if we were to evaluate a 0, and on both sides of the 0, the sign were the same, then that identifies an inflection point. If you go from positive to positive, crossing a 0, you're not changing direction, it's simply an inflection, or from negative to negative. That would show up in the second derivative test as an output of 0. In our calculations, we have outputs 1 negative, we definitively know that's a maximum, 1 positive, we definitively know that's a minimum. If we had an output of 0, a 0 output in the second derivative test could be a maximum, a minimum, or an inflection point. So the second derivative test has a limitation. When the result is 0, you don't know exactly how to interpret that result. In our case, we don't have a result of 0. We've simply identified a maximum and a minimum, and comparing to the results of our sign diagram, we see the same results as we should. We're evaluating the same function. -1 is a maximum, and 0 is a minimum. So we can evaluate stationary points using either the sign diagram test based on the first derivative, or the second derivative test, which uses the second derivative to evaluate the zeros identified from the first derivative. We'll end this video here, and in the next video we'll continue with our analysis of stationary points.